Welcome back to our video series exploring Verilog HDL. The last video we have discussed gate level modeling, data flow modeling. So in this video we are going to discuss behavioral modeling. First we will discuss structured procedures. There are two structured procedures in Verilog, always and initial. These statements are two most basic statements in behavioral modeling. All other behavioral statements can appear only inside these structured procedure statements. Each always and initial statement represents a separate activity flow in Verilog. Each activity flow starts at simulation time 0. The statements always and initial cannot be nested. That's an important point, you have to remember that. First we will discuss initial statement. So all statement inside an initial statement constitute an initial block. An initial block starts at time 0, execute exactly once during a simulation, and then does not execute again. The initial block are typically used for initialization, monitoring, waveforms and other process that must be executed only once during entire simulation run. Here is an example of how we can use this initial statement. I have defined a variable count of register type 4-bit. Initial, if multiple statements are there in initial block, we have to use begin and end. So initial begin, I have initializing count to 0, count equal to 0. Then I am using while loop, while count less than 10 begin, display count value, count is equal to count plus 1. I am incrementing that count value by 1, and hashtag 1 is delay of 1 time unit. This looping of while loop we will discuss later, and also this display function we also discuss later. Now always statement. All statement inside an always statement constitute an always block. An always block starts at time 0. Execute the statements in the always block continuously in a looping fashion. This statement is used to model a block of activity that is repeated continuously in a digital circuit. Example is clock generator. Here is an example of clock generator. Module clock gen, output clock, and that output is register type, that is reg clock. Initial, I have declaring initializing the clock value to 0, and always hashtag 10 clock equal to negation of clock. Every 10 time unit the clock value is negating. Always means it will execute continuously in a looping fashion. So after every 10 time unit the clock value get negated, and I am calling after 100 time unit I am calling the finish function to terminate the simulation. Then we will discuss procedural assignments. Procedural assignments update values of register, integer, real or time. These are unlike continuous assignments discussed in data flow modeling, where one assignment statement can cause the value of RHS expression to be continuously placed onto the LHS. There are two types of procedural assignments, blocking and non-blocking. First we will discuss the difference between continuous and procedural assignment. Continuous assignments assigns value primarily to nets. Variables and nets continuously drive values on port. Used to infer combinational circuits, assignments occurs whenever the value of RHS of the expression changes as a continuous process. Procedural assignments assigns values primarily to variables. Results of calculations involving variables and nets can be stored into variables. Used to infer both sequential and combinational circuits. The value of the previous assignment is held until another assignment is made to the variable. Then we will discuss the two different type of procedural assignments. First we will discuss blocking assignments. Blocking assignment statements are executed in the order they are specified in the sequential block. A blocking assignments will not block execution of statements that follow in a parallel block. We will discuss what is sequential block and parallel block later. The equal operator is used to specify these blocking assignments. Here is an example of a blocking assignment. I have declared A, B, C as registers. Then always at * begin C is equal to A and B. That is blocking assignment statement. I am calling the display function to display A, B and C. Then initial begin, I am initializing the values of A, B. A is equal to 0, B is equal to 0 after 5 time unit, A is equal to 1, and after another 5 time unit I am calling finish. Here that always at of * we will discuss later what that line is meaning by. The next one is non-blocking assignments. Non-blocking assignments allow scheduling of assignments without blocking execution of the statement that follow in a sequential block. A less than or equal to operator is used to specify the non-blocking assignments. Non-blocking assignment statements are executed last in a time step in which they are scheduled. Application of non-blocking assignment is that they are used as a method to model several concurrent data transfer that takes place after a common event. We will discuss what is an event is. Here is an example of non-blocking assignments. I have defined A, B, C as registers. Always at % of clock, begin A less than or equal to B, C less than or equal to A, end. Which means that C is not holding the value of B here. It is holding the value of A. That assignment operation will take place at the end of the time step. So A will, at the end of the time step, A will get the value of B and C will get the value of A. So initial begin clock equal to 0. For hour is another looping statement that is available in Verilog. We will discuss that later. For hour #5 is I am giving 5 time unit delay, then clock is equal to negation of clock. This is a simple example of giving the value of a register to another register. Then one of the important concept is timing controls. In Verilog, if there are no timing control statements, the simulation time does not advance. Timing control provide a way to specify the simulation time at which procedural statements will execute. There are 3 methods of timing control: delay based timing control, event based timing control, level sensitive timing control. We will discuss each one by one. First we will discuss delay based timing control. Delay based timing control in an expression specifies the time duration between when the statement is encountered and when it is executed. This can be specified by a number, identifier, or a min, typical, max expression. There are 3 types of delay control for a procedural assignments: regular delay control, intra-assignment delay control, zero delay control. The first one is we are going to discuss is regular delay control. So regular delay control is used when a non-zero delay is specified to the left of a procedural assignment. Here is an example. I have defined 2 parameters, latency and delta. Latency have value 20, delta have a value of 2. I have defined 5 registers X, Y, Z, P, Q. Initial begin, I am defining X equal to 0, which have no delay. #10 Y is equal to 1. That is delay control with a number, that is 10 time unit I have given. #latency Z is equal to 0. That latency is a parameter having a value of 20. So delay control with an identifier. #latency plus delta. That is delay control with expression. Then minimum, typical and maximum we can represent it using 4:5:6, which is 4 is minimum value, 5 is typical value, and 6 is the maximum value. The next one is intra-assignment delay control. Instead of specifying delay control to the left of the assignment, it is possible to assign a delay to the right of the assignment. Here is an example of intra-assignment delay control. I have defined 3 registers X, Y, Z. Intra-assignment delays is defined. We have already discussed that the intra-assignment delay is specified to the right of the assignment operator. So X equal to 0, Z is equal to 0, Y is equal to hashtag 5 X plus Z. In that line, the values X and Z are taken at time equal to 0 and evaluate the X plus Z. And then they wait for 5 time unit and then they assign the value to Y. The same program, we can do it in regular delay control. Initial, begin, X equal to 0, Z is equal to 0. I am defining a temporary register temp underscore XZ, which evaluates the X plus Z, and then hashtag 5Y is equal to temp underscore XZ. Take the value of XZ at the current time and store it in the temporary variable. Even though X and Z might change between 0 to 5, the value assigned to Y at the time 5 is unaffected. It is same as the previous code, but this is intra-assignment delay and this is regular delay. Then the next one is zero delay. Zero delay control is a method to ensure that a statement is executed last after all the statements in that simulation time are executed. This is used to eliminate a race condition. However, if there are multiple zero delay statements, the order between them is non-deterministic. Here is an example. In initial begin block, I have initialized X equal to 0 and Y equal to 0. In another initial block, I have defined hashtag 0 X equal to 1, that is 0 delay control, and hashtag 0 Y equal to 1. Using of hashtag 0 is not a recommended practice because of that non-deterministic thing. Then the next one is event-based timing control. An event is the change in the value of a register or a net. Events can be utilized to trigger execution of a statement or a block statements. There are 3 types of event-based timing control: regular event control, named event control, and event or control. We will discuss each one by one. Regular event control. The @ symbol is used to specify an event control. Statements can be executed on changes in signal value or at a positive or negative transition of a signal value. Here is an example how we are giving this regular event control. At of clock Q equal to D. This Q equal to D is executed whenever the signal clock changes value. The next one is at of post clock Q equal to D. This Q equal to D is executed whenever the signal clock does a positive transition, that is from 0 to 1 or 0 to X or 0 to Z or X to 1, Z to 1. The next one is at negate clock Q equal to D. This is executed when the clock signal does a negative transition and Q is equal to at of positive edge of clock D. D is evaluated immediately and assigned to Q at the positive edge of a clock. That is the difference between at post edge of clock Q equal to D and Q is equal to at of post edge of clock D. Event based timing control. The next one is name event control. Verilog provides the capability to declare an event and then trigger and reorganize the occurrence of that event. The event does not hold any data. A name event is declared by a keyword event. An event is triggered by the symbol arrow. The triggering of event is recognized by @. Here is an example. It's an example of a data buffer storing data after the last packet of data has arrived. I'm declaring an event named received data, always at postage of clock begin if last data packet, that is if last data packet value is high, then I am triggering the event using arrow key, and event name is received data, and I am ending that always block, and another always block at received data. It awaits triggering of an event. Here event is received data, that is whenever that received data event is triggered, this always at received data block will execute. That is data buff is equal to concatenation of data packet 0, 1, 2, 3 will get assigned to data buff if that event is triggered. Then event or control. Sometimes a transition on any one of the multiple signals or events can trigger the execution of statements or a block of statements. The list of events or signals expressed as OR is known as sensitivity list. Here is an example. Here it is a example of a level sensitive latch with asynchronous reset, always at reset or clock or D, which means that it will wait for reset or clock or D to change. If one of the signals is changing, then that always block will execute. If reset, then Q equal to 1, Q equal to 0, else if clock is there, then Q equal to D. This is simple level sensitive latch. The same code we can represent with a comma separated in the sensitivity list. Instead of reset or clock or D, we can represent it as reset comma clock comma D. It is the same meaning as the previous one. When the number of the input variables to a combination logic block is very large, then this sensitivity list can be very lengthy. And if you forgot to write some inputs inside this sensitivity list, that particular working of the block is not up to the mark. So to solve this problem, Verilog HDL contains two special symbols, @* and @**. Both the symbols exhibit the identical behavior. So instead of writing reset or clock or D, we can simply represent it as @*. If number of input, all the input you have to represent inside the sensitivity list, you can simply write it as *. Then level sensitive timing control. Verilog allows level sensitive timing control, that is the ability to wait for a certain condition to be true before a statement or a block of statements is executed. The keyword wait is used for level sensitive constructs. Example always. If count enable is high, up to that it will wait. That is wait of count enable. Whenever the count enable is high, #20 count is equal to count plus 1 will execute. Then we will discuss these conditional statements and looping in the next video. Thank you.